Hi all and welcome to Tech Times. Today we are going to start video tutorial on Kafka. Just to give you a highlight of what we are going to cover today. First we will understand need for distributed messaging systems like Apache Kafka. Then what is Apache Kafka? We'll also cover what all messaging systems are available and how Apache Kafka is different from them. We will go through high level architecture of Apache Kafka. So let's understand why there was a need of distributed messaging system. Way back in 2009, LinkedIn was facing a lot of issues while processing messages in a speed that they were arriving, causing a latency in data. We have some examples of what actual data volume of LinkedIn was dealing with. So with respect to volume, LinkedIn was dealing with 1.4 trillion of messages every day. More than 750 terabyte of messages were consumed and 500 million users were using it on daily basis. Regarding the velocity, we have millions of messages generated per second and 3 GB of data transferred per second. Then there is a variety of messages which LinkedIn deals with. What I mean by variety is it deals with different types of data like text, images, videos, and there are many other type of messages LinkedIn deals with. So if you conclude all this is very huge data to be processed, and to get a near real-time experience to the end users, LinkedIn needs this data to be processed near real-time. So LinkedIn came up with a solution that can process these messages with high throughput and it can be scalable as well. So that was later named as Kafka. So what is Apache Kafka? Apache Kafka is all about data. It is about getting that data from one place to another in rapidly, reliably, and scalably format. So Apache Kafka is a messaging system, but unlike others, it is designed for high throughput use cases where large amount of data is transferred in a scalable way. So why we need Apache Kafka? That one question everyone has, right? So if we look at any enterprise solution in the market, they generate a lot of data in format. There are various formats in which data is generated, like we have logs, we have messages, we have binary objects, and all these applications are generating data at incredible rate. This can strain our existing data stores and often require to add more data stores to take on the load. Apart from that, if our business change and there is a need to process different type of data like unstructured data, images, videos, and if our existing data structure doesn't support such kind of data, this can create more challenges in future. There are various tools available in the market to make this complex topology possible. So one is data replication and log shipping. So what data replication is, it's just copying of data from one database to another so that all the users get same type of information who are accessing those databases. Log shipping works in a similar fashion. This is very commonly used enterprise application, but there are some limitations to it. It can only work between database to database. Therefore, it can't work across vendors. If you are dealing with heterogeneous data, then it becomes a limitation. There is very tight coupling between these applications. Like there is a schema. If there is any change in schema, then it will have direct impact on replication. So if your requirement change and you change any schema, it will have a ripple effect on your system, and maintaining those systems can be a challenge. For log shipping, performance is one of the biggest challenge, but it depends on how much log you're trying to ship and at what frequency you're trying to ship it. So these are something drawbacks of database replication and log shipping. So let's go to next one. So next one is ETL. What ETL is, it is extract, transform, and load. Just to give you a short description of what ETL means is, extract means we are pulling the data from sources. It can be any type of data source. It can be Oracle, it can be SQL, or it can be file. Then we have to transform that data to get some meaningful information out of it for our business purpose. This step is like data enhancement. Now, once that data is transferred, we have to load that data into some target database or file or any other system where you want to load that data. So this complete process of end-to-end movement is called ETL. So ETL is widely used by data engineers across industries to manage their data. There are various tools available in market which you can use to achieve this. So one drawback of this tool is that it is licensed. So all the powerful tools which are available in market are all licensed. Therefore, there is a cost associated with implementation of ETL. Also, we need to hire developers who are excellent in using these tools and developing our logics. So there is again a cost associated, developer cost associated with this approach. As the data and the business requirement increase, more and more logic we write, more and more jobs we create to process this data. So the third drawback is scalability. So once our data increases and jobs increases, our centralized systems, all the pressure goes on a centralized system and it will performance will degrade. So how to resolve this issue? It can be resolved in two ways. Either we increase the hardware of our existing system, or we add more systems in parallel to process the data in parallelly. So, but that will increase the complexity. So last one is the messaging system. But this messaging system we will understand more in more details in our upcoming slides. Messaging is very important for moving data between applications. However, when it comes to large scalable solutions, existing messaging systems can struggle. Sometimes message broker who handles messages becomes a bottleneck for processing the data. Also, there are a lot of other factors which can determine performance and reliability of messaging systems, like size of message. Large data packets can put additional stress on message broker, and it may be a challenge because you may not be able to control the message coming from the source. Also, there is an expectation that consumer consuming the message as soon as it is available. This may not be possible because due to many reasons, like consumer is busy or down and that message might get lost. There is another possibility that consumer might not process the message or it processes the message incorrectly and want to retrieve message again, but it is not possible since message is already deleted post the read from broker. Let's understand it better with visualization. Consider we have a publisher, broker and subscriber. Now don't get confused with these names. Let me explain it to you. We have a publisher who is publishing the messages. Then we have a subscriber who is consuming the messages. In between them, there is a broker who is just like acting an agent between them and transferring the messages sent by the publisher to the subscriber. In an ideal situation, this system will work without any issues, but what if there are increase in volume at publisher? In this case, publisher will blast messages to the broker, and if there is no threshold or throttle implemented, broker won't be able to handle such load of messages. Most of the messaging system, there is only single node and it uses a local storage to store the messages. This isn't a problem since messaging systems are very fast and pass messages immediately to the subscriber without impacting their local storage, unless our subscriber consuming the messages at slower rate. If our messages are not consumed at faster rate, the speed at which publisher is producing the messages, then there will be a huge workload on broker. This can cause disastrous implications on broker since the disk may get full and publisher can't publish messages to the broker and causing an error to an application. In another approach, consider if our consumer fails in between due to whatever reason and incorrectly process the data. Consumer can't go back to broker asking for that message since it is not available there. Of course, consumer can save that message somewhere on their disk and reload them, but it's not always the case. There are different ways in which we can handle and manage these kind of scenarios, but let's not go in deep into them, and let's deep dive into Apache Kafka architecture. Apache Kafka is publisher subscriber messaging system. In publisher subscriber model, a publisher creates some data and sends it to some location where interested and authorized subscriber can consume the data and process it. In Apache Kafka, we call publishers as producers and subscribers as consumers. Producers and consumers are nothing but applications that we can write using APIs that are already provided by Apache Kafka. These producers and consumers can consume and produce the data after that. Now producers send some data to a location like I mentioned earlier. This some location in Kafka is called as topic. Topic is just a collection or grouping of messages. In each topic, there is a specific name associated to each topic. Producer uses the same name to produce the message and consumer uses the same name to consume the message. Now all the topics are placed on a server. That server is called as broker in Apache Kafka. I think we have covered a lot in terms of terminologies. So let's have a recap. Producers create a message and deliver it to a topic. We can easily write a producer API application using APIs provided by Apache Kafka. Consumers consumes the message from the topic. Similar to producers, there are APIs provided for consumers as well. And we can write easily using that and create our own consumer application. Topic is collection of messages and broker is collection of topics. Now let's move forward. Now Kafka Broker is an application which runs on any physical or virtual server. This application has access to this file system and stores the messages on the local server. Like any other application, we can run multiple instances of broker on the same machine as well, or brokers can run on different machines as well. It totally depends on infra and the need of project. Each broker has access to their own file systems. If the multiple brokers are running on same server, still they will have different file systems so that they don't interfere with each other. Now we already know that Apache Kafka has very high throughput. Now what high throughput means? High throughput means that efficiently it can distribute its load and process it in parallel across multiple nodes. Now how Apache Kafka achieves that high throughput? In Apache Kafka, you can increase number of brokers by any number based on your need, and it will increase the throughput of the messages. All the messages are stored on broker itself, so it won't impact any producer or consumer if we keep on adding additional brokers. It will just share the workload of existing brokers and increase the throughput. Like I said earlier, multiple brokers can run on same machine or on different machine, but it totally depends on what your need is and what infrastructure is available. All this set of brokers is called a cluster. So if you have multiple brokers, then combining all those brokers, we call it as a cluster. So there can be many brokers in cluster. There are thousands and thousands of brokers in real time in very big companies like LinkedIn. Now, if you have a single broker, then it is called as a cluster of size 1. If you have multiple brokers, if you have two brokers in that cluster, then we call it a cluster size of 2 and so on. Now we know that what is a cluster. So how this cluster works. Now actually cluster is a group of different brokers. Now how these different brokers work together to achieve a single task. Now this concept is called as distributed system. What distributed system is? A distributed system is a collection of resources working together to achieve same goal. They consist of multiple worker nodes. In our case, we call it as broker. They coordinate with each other to ensure consistency and progress towards the goal. This should be managed properly so that all the brokers are properly utilized. No broker should be underutilized. All the brokers should have some tasks and all those tasks should be monitored properly. Now all this is communicated within the cluster by a controller that exists within the cluster itself. Now, all those details we'll cover in our upcoming sessions. The last point which I think we should cover in our architecture is Apache Zookeeper. Now, Apache Zookeeper also plays a very important role in total infrastructure of Apache Kafka. Now, what Apache Zookeeper is, it is used, like Apache Zookeeper is used at multiple infrastructures. Like it is used in Hadoop as well, it is used in Kafka as well. Now, to cover Apache Zookeeper in detail, we need another course. We cannot cover it in detail in this tutorial. So I will just give you a brief of what Apache Zookeeper is. So Apache Zookeeper maintains metadata of cluster. So how many nodes are there in a cluster, their health status, how many nodes are alive and how many nodes are dead. If any nodes are not responding on time, then it will consider it as down and it will assign those tasks which are assigned to that node to different nodes. So that all this management is done by Zookeeper. And Zookeeper itself can be a distributed system as well. Now, either we can have a single machine as a Zookeeper, we can have multiple machines as a Zookeeper as well. They are internally connected, but they are working towards a single goal of managing metadata of the cluster. Now, Apache Kafka doesn't require or doesn't have much tasks assigned to Zookeeper. So a single Zookeeper machine can also manage a whole lot big cluster as well. So now let's complete our architecture and see how it looks. As you can see, now we have added Apache Zookeeper as well. So we have producers, we have brokers, we have consumers. The messages are flowing. Inside every broker, there are topics, and all this cluster is managed by Apache Zookeeper. So this is a basic overview of how Kafka architecture looks like. I think we have covered a lot in this tutorial. We will go in more details in our upcoming sessions. We'll go do a deep dive in core components like broker, topics, and partitions. Okay, that's it for today. Thanks for watching. Do like, share, and subscribe to our channel.